Hi boys and girls, this is lecture 1.9, the last lecture in Unit 1, the topic Geometry and Trigonometry. You see here on this first page all of the geometry we're going to discuss in this lecture. A series of geometric shapes, as you can see, and the corresponding formulas. When you're given a problem requiring a geometric formula on the AP exam, often the formula is given to you. If it was something like volume of a pyramid or a cylinder or something like that, you would be given the formula and would just need to know how to manipulate it to solve for the variable specified. Which ones should you have memorized? Well, it's not a bad idea to know all of them, of course, but you are going to be expected to know anything having to do with a square, rectangle, triangle, circle, perhaps a few more basic relationships as well. But be familiar with all of these formulas and know how to use them correctly, and that is your responsibility as far as geometry is concerned. And now on to trigonometry. Trigonometry is the study of how the sides and the angles of a triangle relate to each other. Ratios of a right triangle's side lengths are used to define the 6 trigonometric functions: sine, cosine, tangent, cotangent, secant, and cosecant. And you can see those relationships demonstrated here. In reference to the angle theta, the ratio of the opposite side to the hypotenuse is called sine. The relationship of the adjacent side to the hypotenuse is called cosine. The ratio of the opposite side to the adjacent side, tangent, etc. And the other 3 trigonometric ratios are listed here. You've probably seen the word SOHCAHTOA before, and that's a mnemonic to help you remember these first 3 trigonometric ratios. The first letter, S, stands for sine, and then opposite over hypotenuse, cosine, adjacent over hypotenuse, and then tangent, opposite over adjacent. Now let's use trigonometric ratios to find trigonometric values. Given that secant theta is 12 over 5, find the values of the other 5 trigonometric functions of theta. Well, we need to start with the fact that secant theta is this relationship, hypotenuse over adjacent. Since in this case that's 12 over 5, that means in reference to the angle theta, the hypotenuse is 12 and the adjacent side is 5. Of course, we also need to know the third side of this triangle, and we'll use the Pythagorean theorem to find that. We know the hypotenuse squared is 144 is equal to 5 squared, 25, plus the missing side, which we'll call x squared. When you subtract 25, you get 119 equals x squared, and then we do need to take the square root of both sides, which gives us the irrational number square root of 119. We'll just let that be the length of the side for now, because after all, the square root of 119 is the exact value, whereas a decimal approximation would not be exact. Now, with all 3 sides labeled, let's list the trigonometric ratios. Sine of theta, opposite over hypotenuse. So that's going to be the square root of 119 over 12. Cosine of theta is adjacent over hypotenuse, 5 over 12. Notice that's the reciprocal value of secant. Tangent of theta is opposite over adjacent. So that's going to be the square root of 119 over 5. Cotangent of theta is going to be adjacent over opposite. So that's going to be 5 over the square root of 119. Then we already know what secant is. Secant theta is 12 over 5. And then cosecant of theta is the reciprocal relationship of sine, and so that is going to be hypotenuse over opposite, which is 12 over the square root of 119. And those are the 6 trigonometric ratios with relationship to theta based on the initial information that was given regarding secant. I'm just going to leave these denominators unrationalized for this particular problem in order to demonstrate these processes. In this next example, we're asked to solve triangle ABC. That means, given the information that we have here, one angle measure and one side length, find the other angle measure and the other two side lengths. Knowing what we know about trigonometric relationships, we will be able to do this. But let's start with the third angle measure. This should be simple to do, and we don't even need trigonometry. Since all three angles add up to 180, and we know two of the angle measures, we'll be able to easily find the third. We can add the two angle measures that we have. 28 plus 90 is 118. And then subtracting that from 180 will give us the third angle measure. 180 minus 118 leaves 62 degrees. Therefore, angle B is 62 degrees. Now let's solve for one of the sides, and we can start with the hypotenuse, which I'll label small letter c. And in reference to the angle 28, the side opposite and the hypotenuse gives us the sine ratio. So let's use sine of 28 is equal to 15, the opposite side, over c, the hypotenuse. Given this relationship, we'll be able to solve for c. First, cross multiply. We'll have c times sine of 28 is equal to 15, and we can solve for c by dividing by sine of 28. So once we have this set up, let's get the calculator. Make sure that your mode is correct. When you're switching back from radians to degrees, it's very easy for it to be in the wrong mode when you're calculating a value. Since we're using degrees in this problem, the calculator needs to be in degrees. We need 15 divided by sine of 28. And as you can see, this value is very close to 32. So we'll let the small letter c be 32, the length 32. And now all we're missing is the third side, which we'll call lowercase b. Now, if I'm using 28 degrees, the opposite side and the adjacent side, that's the tangent ratio. Of course, at this point, you could use the other angle, you could use the hypotenuse. There are several relationships that would allow you to solve for b, but I'll just stick with the original given information, 28 and 15. And therefore, using the tangent ratio will let us solve for lowercase letter b. The tangent of 28 degrees is 15 over b. Once again, cross multiplying will give us b times tan 28 is equal to 15, and then dividing both sides by tan 28 will give us a setup that reveals the value of b. In our calculator then, we need 15 divided by tangent of 28 to get the remaining side. And that is about 28. And so now once you have b, you have all three sides of the triangle solved for, all three angles. You have solved triangle ABC. Speaking of radian measure, angles can also be measured in radians. Because the circumference of a circle is 2 pi r, there are 2 pi radians in a full circle. Let's learn to convert between degrees and radians, and here are the two conversion formulas that you will use. Let's convert negative pi over 12 radians to degrees. This is the formula that we'll use. We'll multiply by 180 over pi. The pi's cancel, of course, and 12 goes into 180 15 times, so this is equivalent to negative 15 degrees. Now let's convert from degrees to radians. We're going to use this formula. 125 degrees times pi over 180. Now, when you reduce this fraction, it becomes 25 pi over 36 radians. Notice here I have a diagram which has degree and radian measure of special angles. Special angles are any multiples of 30 degrees, 45 degrees, 60 degrees, of course 0, 90, 180, 270, etc. Those are the special angles that we deal with most frequently. Even though it is helpful to know the relationship between degree and radian measure, calculus will require the use of radian measure almost exclusively. General definitions of trigonometric functions. Let theta be an angle in standard position. Standard position meaning that one side of the angle lies along the x-axis at the 0 position, and let xy be the point where the terminal side of theta intersects the circle x squared plus y squared equals r squared. So here's the angle and the terminal side of the angle intersecting at the point xy, which is on this circle of radius r. Notice a triangle is formed, a reference triangle. This angle corresponds to the angle theta, and the lengths of the sides of this triangle are x, the horizontal distance, y, the vertical distance, and the hypotenuse is r, the radius of the circle. With these three lengths, the 6 trigonometric functions of theta are as follows. Sine of theta would be y over r, cosine of theta, x over r, tangent, y over x, cosecant is r over y, secant, r over x, and cotangent is x over y. So notice with this reference angle drawn, we are able to generate the 6 trigonometric functions from an ordered pair. So let's do that here in this example. If the point -4, 3 is the terminal side of angle theta, evaluate the 6 trigonometric functions of theta. So once again, the terminal side of the angle is intersecting this circle at the point -4, 3. So let's label the sides of the triangle. We have the horizontal distance -4, the vertical distance 3, and using the Pythagorean theorem, we'll be able to find the hypotenuse. -4 quantities squared plus 3 quantities squared is going to be r squared, our hypotenuse. 16 plus 9 is r squared, and of course that's 25. Therefore, r for this circle is 5. Now we have the 3 sides of the triangle labeled. We're able to list the 6 trigonometric functions. Sine of theta is opposite over hypotenuse, which is 3/5. Cosine of theta adjacent over hypotenuse, -4/5. Tangent of theta is going to be opposite over adjacent, which is -3/4. Cotangent of theta is going to be adjacent over opposite, -4/3. Secant of theta is hypotenuse over adjacent, so 5 over -4, or -5/4. And finally, cosecant theta, which is hypotenuse over opposite, 5 over 3. Here we find a plethora of information to assist us in finding trigonometric values for special angles. Special angles like 30, 60, 45, any multiples of those, 0, 90, 180, 270, etc. The ones that we deal with most frequently. Knowing 2 special triangles, the sine and cosine graphs, and reference angle relationships will provide all the information you need for obtaining trigonometric values. Now notice I also have the unit circle listed here. This is another way to know all of those values as well, and possibly you have that memorized. But I'm going to use the 2 special triangles listed here, the sine graph, the cosine graph, and reference angle relationships to find the values I need. Why? Because I don't want to depend on my memory. What if the one value I need is the one that I have forgotten? I would rather be able to generate that information in case I forget something I memorize, which is why I do not have the unit circle memorized. So let's practice evaluating trigonometric functions, starting with getting used to dealing with radians rather than degrees. Pi over 6 is what in degrees? Remember that pi is 180, so 180 divided by 6 means that pi over 6 is the 30-degree angle. Well, I'm going to go over here and use this tool, which is a 30, 60, 90 triangle to assist me in evaluating this trigonometric function. I know that in this triangle, the side opposite 30 degrees is 1, the hypotenuse is 2, and the other length is the square root of 3. This is the relationship between the 3 sides of this triangle all the time. Now notice that once I've labeled these 3 sides, I can tell you any trigonometric value for 30 degrees and 60 degrees. So it has a lot of information in case I need it. But at this point, I'm looking at a 30-degree angle, pi over 6, and I want the tangent, which is opposite over adjacent. So it's 1 over the square root of 3. and I'll just leave it unrationalized there. Now we want cotangent of pi over 4. First of all, pi over 4 is what angle in degrees? 180 divided by 4 is 45. Therefore, I go over here and use this tool, the 45, 45, 90 triangle, where the sides also have special relationships. 1, 1, square root of 2. Cotangent is adjacent over opposite, and so the cotangent of 45 degrees, 1 over 1, which is 1. Now notice I have a lot of other information here as well, but of course it gives me the information I need. Cosecant of pi over 3, 180 divided by 3 is 60 degrees, so once again I use this triangle, the 30, 60, 90. And since I know the relationships of the lengths of the sides, 1, 2, square root of 3, I can generate any trigonometric ratio for 60 degrees. But since I need cosecant, which is hypotenuse over opposite, I know that the cosecant of pi over 3 is 2 over the square root of 3. Now let's evaluate some trigonometric functions that are not in the first quadrant. To help me with this, I'm going to bring over a little coordinate plane and place this angle where it belongs, and therefore generate the reference triangle as well, which will help me evaluate this function. We start with the 0 position and start moving in a clockwise direction since this is a negative 2 pi over 3. Moving negative 1 pi over 3, 60 degrees, negative 2 pi over 3, another 60 degrees, takes me to about this location. Now, as I draw the triangle, remember that reference triangle is always drawn to the x-axis. This is a 60-degree angle, pi over 3. So the relationships I need come from the 30, 60, 90 triangle. Since this is 60 degrees, I know that this is the square root of 3 side, but it's negative here in the third quadrant. And here is the 1 side, but it's negative here in the third quadrant. The hypotenuse, of course, is always positive. Now, with these lengths drawn, again, generated from the 30, 60, 90 triangle, I can find the tangent of this angle. Opposite over adjacent. Negative square root of 3 over negative 1 is a positive square root of 3. Now let's look at cosecant of 17 pi over 6. Once again, I need to use my handy little coordinate plane, which I didn't realize I had moved over there, but we'll put another one here. And remember that in this case, we have a positive direction, but it looks like we're going through more than one rotation around the coordinate plane. Since the denominator is 6 and a full rotation is 2 pi, 12 pi over 6 is one full rotation. So we are going all the way around the circle, but then another 5 pi over 6, which takes us into the second quadrant to about this location. So there's the terminal side of this angle. Drawing the reference triangle to the x-axis gives us a reference angle of pi over 6, which is 30 degrees. Now once again, I know that the lengths of the sides of the 30, 60, 90 triangle are going to help me evaluate this. This is going to be a 2 because it's the hypotenuse, and opposite the 30-degree angle is 1. This is the square root of 3 side, but it's negative here in the second quadrant. And so now to get cosecant, which is hypotenuse over opposite, that's going to be 2 over 1 in the second quadrant, and so this answer is 2. And now for the final one that I'm going to evaluate, cosine of 7 pi over 4. Let's get a coordinate plane and see where this is located. Since the denominator is 4, a full rotation would be 8 pi over 4. So 7 pi over 4 is almost all the way around. 0 pi over 4, 1 pi over 4, 45 degrees, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. So it's the 45-degree angle in the fourth quadrant, and here is the reference triangle. So I'm looking at pi over 4 relationships, which, as we remember, the sides are 1 positive for this side, but negative for this side. And of course, the hypotenuse is always positive, and that's the square root of 2. Now that I have all 3 sides labeled, I'm able to say what the cosine of 7 pi over 4 is. Since it's adjacent, 1 over hypotenuse square root of 2, this value is 1 over the square root of 2. More often in calculus, you'll be asked to find an inverse trigonometric value. That is, find an angle that corresponds to a given value. For example, the inverse tan of the square root of 3 is really asking this question. The tangent of what angle is the square root of 3? We may have this memorized, but in case it's the one factoid we have forgotten, let's practice generating the information if needed. I look at the value given, square root of 3, and I recognize that it comes from the 30, 60, 90 triangle relationships. So let's use this triangle to help us figure out what angles have a tangent of the square root of 3. Once again, labeling the three sides, 1, 2, square root of 3. I'm looking for an angle whose opposite over adjacent side is the square root of 3. You can see that that's the 60-degree angle. The square root of 3 over 1 is its tangent relationship, and that is the square root of 3. So in this case, 60 degrees is one of our answers, and we're going to write that as pi over 3 in radians. However, we need to realize that that's not the only answer, because in the coordinate plane, if we're looking for, let's say, just all of the angles that satisfy this given condition from 0 to 2 pi, there is another place where tangent of theta is equal to the square root of 3. Remember, it's a 60-degree reference angle, so we have that reference angle here in the first quadrant, which has a positive pi over 3. It could be in the second quadrant, the third quadrant, or the fourth quadrant. Since it's a positive square root of 3, we're looking for the other place where it's going to have a positive value, where tangent has a positive value. Well, let's look in the second quadrant. If this is your angle and tangent is opposite over adjacent, you would have a positive value over a negative value. That's a negative tangent value. If you look at the third quadrant, reference triangle, you would have, in reference to this angle, opposite over adjacent, negative over negative. So in the third quadrant, tangent is also positive. Of course, it's positive in the first quadrant, but you can see in the fourth quadrant it is not positive because opposite negative over adjacent positive would give you a negative value. So we discover that tangent is positive in the first and in the third quadrant. So we've listed the angle that shows up in quadrant 1. What is the pi over 3 angle that shows up in quadrant 3? Well, remember, this is 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. That's the pi over 3 reference angle in the third quadrant. So those are the two answers for letter A. Now let's do letter B. We're actually being asked the sign of what angle or angles is equal to negative square root of 2 over 2. Now, we need to recognize this as the rationalized version of negative 1 over the square root of 2. I should have made an equal sign there. And recognize that that also comes from the 45, 45, 90 triangle. So let's grab one of these guys and figure out what angle will give us a sign of negative 1 over the square root of 2. Since there's really only one angle in the triangle, the 45-degree angle, we probably already know what it is. Labeling the sides, 1, 1, square root of 2. And you can see that since sine is opposite over hypotenuse, 45 degrees is the reference angle that gives you the square root of 2 over 2 value. However, we're looking for a negative sign value. Where is that occurring in the coordinate plane? Now, we could use our little reference triangle coordinate plane, and I am going to do that here. Reference triangle in the coordinate plane. Remember, we have a 45-degree angle here, 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 here. Sorry. Let's see which of these triangles will have a positive sign value. Yes, in the first quadrant for sure. Opposite over hypotenuse. Remember, the hypotenuse is always positive. Notice also in the second quadrant, opposite is positive and hypotenuse is positive, so sine is positive here. In the third quadrant, however, the opposite side is negative over hypotenuse, giving us a negative sign value. And similarly, the vertical distance, which is opposite, is negative over hypotenuse, giving us a negative sign value. So sine is negative in the third and the fourth quadrants. Therefore, we need the 45-degree angle that is showing up in the third and fourth quadrants. So pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4 in the third quadrant, 6 pi over 4, 7 pi over 4 in the fourth quadrant. So these are the two answers to this question. Now another way to look at this, since this is sine, is look at your sine graph. Notice that it's positive in quadrant 1 to pi over 2 and quadrant 2 up to pi. But from pi to 2 pi, it's negative. So in the third and fourth quadrants, it's negative. So the graph also helps you determine this information. Now let's look at inverse cosine. Cosine of what angle is negative square root of 3 over 2? Now, we should recognize that these numbers are coming from our 30, 60, 90 triangle, and I'll just use the one that's here. We're looking for the angle where the adjacent over hypotenuse is square root of 3 over 2. And that's this angle, 30 degrees, adjacent over hypotenuse. So the reference angle is pi over 6, which is 30 degrees. However, this is a negative value, so we need to know where cosine is negative. Let's go, since it's cosine, let's go quickly to the cosine graph and see where it's negative, in which quadrants. The first quadrant from 0 to pi over 2, cosine is positive. The second quadrant from pi over 2 to pi, negative. From pi to 3 pi over 2, negative. And then in the fourth quadrant, positive. Since we have a negative value, we need the pi over 6 reference angle in the second quadrant and in the third quadrant. What are those values? Let's grab a coordinate plane and find out where they are. Pi over 6 is 30 degrees. So we start with, of course, 30 degrees here. We're going to have pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6 here is in the second quadrant, 6 pi over 6, 7 pi over 6 here in the third quadrant. So since in the second and third quadrant cosine is negative, those are our two answers, 5 pi over 6 and 7 pi over 6. And now for the last problem. They're asking for cosine of what angle is equal to 0. Well, we're not going to get that information from our special triangles. We just need to look at our cosine graph. Where is cosine equal to 0? At pi over 2 and at 3 pi over 2. So those are your two answers. Now, again, we're assuming that we're looking for answers within the range of 0 to 2 pi, which is one rotation around the coordinate plane, but pay attention to instructions to see how many values they want you to generate. On this page, we're going to take a look at a few trigonometric identities. Listed below are the fundamental trigonometric identities used in calculus. You won't need to prove them, verify them, or otherwise manipulate them. You'll just need to have them memorized. On the bright side, there are far more trigonometric identities than those listed on this page. But these are the ones that show up with frequency in calculus, so we should focus here. Starting with the reciprocal identities. Cosecant of theta is 1 over sine theta, and of course sine theta is also 1 over cosecant theta. Secant theta is 1 over cosine theta, and of course cosine theta is also 1 over secant theta. Cotangent theta, 1 over tan theta, and of course tan theta is also 1 over cotan theta. The tangent and cotangent identities, tan theta is sine theta over cosine theta, and cotan theta is cosine theta over sine theta. The Pythagorean identities, sine squared theta plus cosine squared theta is equal to 1, and the two corollary Pythagorean identities, and finally a couple of double angle formulas. I have seen the double angle formula for sine show up occasionally, and very rarely I'll see the double angle formula for cosine show up. This is the list, and we need to be familiar with these identities. Best case scenario, have them memorized in order to be ready for what you need for calculus. For our last trick, we're going to solve a couple of trigonometric equations. Notice I have my little toolbox here handy in case we need some assistance in finding an angle associated with a specific value. Who knows, that might show up soon. First of all, let's isolate x. I have 2 sine x, and if I add square root of 3 to the other side, that equals the square root of 3. Dividing both sides by 2 gives me sine x is equal to the square root of 3 over 2. Well, we've been here before, boys and girls. We know that this value comes from the 30, 60, 90 triangle relationship. So let's grab one of these triangles to help us find the angle measure associated with this value. I label the sides, and I'm looking for the angle that has, since this is a sine, opposite over hypotenuse of square root of 3 over 2. That is the 60-degree angle, opposite over hypotenuse. But as we know, there's not only one place where the sine of x is a positive square root of 3 over 2. It's going to be positive in the first and the second quadrants. So we need the 60-degree angle in the first quadrant, which of course is pi over 3. And we also need the 60-degree angle in the second quadrant. And remember, this is pi over 3, 2 pi over 3 in the second quadrant. That's where sine is positive, in the first and second quadrants. And so these are the two angles that have a sine value of the square root of 3 over 2. Now let's look at letter B. I'm going to factor out a cosine. Cosine of x, and then square root of 2 cosine of x equals minus 1 equals 0. This gives me two factors. I can get values from cosine x equals 0 and from the square root of 2 cosine x minus 1 equals 0. Solving this gives me cosine of x is 1 over the square root of 2. So I'll get angle measures from this equation and angle measures from this equation. Let's start here. This is the easy one because I'm just going to look at the cosine graph. Where is cosine equal to 0? At pi over 2 and at 3 pi over 2. So x can be those two values. And then as I look at my second equation, I am looking for the angle where cosine is 1 over the square root of 2. Of course, this comes from our 45, 45, 90 triangle. And so I grab one of these fellows to help me out, labeling the lengths of the sides, 1, 1, square root of 2. Of course, I'm looking for adjacent over hypotenuse to be 1 over the square root of 2. That angle, of course, is 45 degrees, or pi over 4. But where is cosine positive in the four quadrants? It's positive in the first quadrant and the fourth quadrant. Therefore, I need the first quadrant pi over 4 angle, which of course is pi over 4, but I also need the fourth quadrant pi over 4 angle, and that is 7 pi over 4. So these four answers are solutions to this equation. That's it for this lecture, boys and girls, and that finishes off the Unit 1 lectures. I leave you with one more identity that you need to know how to simplify. God bless you, boys and girls.